So second speaker is Naudts, and he will speak about very interesting geometrical structures again on the manifold of quantum statistics.
Thank you. We had a nice application, but now we go to quite abstract stuff. Although to keep everything comprehensible, I will limit myself to the finite dimensional case, which in practice means I will work with matrices. This is the contents, and I only have 16 slides, so every slide has a title. So don't worry about having, it's heavy stuff, but not too much, I hope. Okay, in this talk I will clarify the content of a paper I published 1 year ago in Entropy. And I will show that by using elements of the Tomita-Takezaki theory, the published work can be clarified, becomes more clear what is going on. But before doing that, I will explain, of course, everything. Before doing that, I will give some comments on what is quantum statistics. Because quantum statistics, I think, should be considered as a generalization of the standard statistics. It's a generalization, means the standard statistics is one particular case of a larger theory, which also includes quantum mechanics, okay? But also many other applications, like we heard one in the previous talk. And the main change, or the main axiom which disappears compared with classical statistics, is that the assumption of a sample space is not made. So we will do statistics, and we don't assume that there is an underlying universe, underlying event space. And in fact, quite many people at this conference, if they, for example, minimize a divergence function, they don't speak about the underlying event space because you don't know how it is in many cases. And so the basic assumption is we don't know whether there is underlying sample space. So the way to go on then is to see that in statistics, random variables are functions of events. If there are no events, you can't do that. And you replace random variables by abstract elements of an algebra. And whatever the algebra is, in principle, you could go on. But there exists a mathematical framework for that quantum statistics, which is made about 50 years ago, and which is based on the theory of C-star algebras and von Neumann algebras. And I will not give definition of that because I will not need it for my exposition. But I will explain, of course, what's the link. In classical statistics, you have a probability measure on the event space, X, sample space, and then you can calculate the expectation of a random variable by integration, okay, that you know. And either you denote that as expectation of the random variable or mu of f, because it depends on the probability distribution. And the point now is that the algebra of all bounded integrable functions is a von Neumann algebra. Although I will not give the definition, but I consider bounded functions, and then for each bounded function you can calculate an expectation value, because mu is a probability function, probability measure. So the generalization is now that the map random variable to its expectation is generalized, and that's what one calls a state on the C-star algebra. The name state, of course, comes from physical state, from quantum mechanics, but that's not important here. So we have some C-star algebra, which is an algebra with a conjugation adjoint. And for each element, and now I changed notation. Instead of f, I use a because we associate that with operators. And the reason is that there's a theorem that you can always represent those algebras cyst algebras as algebras of operators on a Hilbert space. So I have an operator A, which is my random variable, and the only requirement for the expectation value, or two requirements, is if I have a strictly positive or positive operator, then the expectation should be positive. And the second one is the normalization. The identity function has probability 1 or expectation 1. So the normalization, if this is the identity operator, then its expectation should be 1. And those two assumptions suffice to say what's a state of the C-star algebra. And the change of notation also, omega for state is quite common in the theory of C-star algebras instead of using mu for a classical measure. Of course, if my algebra is L infinity, then mu is a state on that algebra. So the classical case is just a special case of the generalization. Okay, from now on, I restrict myself to the algebra of n by n complex matrices, okay, which you all know, properties of that algebra. And then we heard already in the previous talk about density matrix. Every state on that algebra of n by n matrices is determined by a density matrix, which is a positive matrix with trace 1. And it has eigenvalues. If you diagonalize the density matrix, then the eigenvalues stand on the diagonal and sum up to 1. So that gives a probability interpretation. Each eigenvalue is a probability, and the sum of all probabilities is 1. And the relation, the state is then given by the trace of the product of that density matrix with an arbitrary matrix. Okay? That's how the formalism works. And the study of the manifold of all density matrices you can find in textbooks, for example, in the book of Pets, 2008. So the difference with the symmetric positive matrices, which we heard in a previous session, is that here we require that the density matrices are normalized to 1, or the states are normalized, and the manifold is the manifold of all normalized positive matrices. Okay, now comes something which is less usual, and probably it's not what people working with computers will do. I will consider representation of the n by n matrices as n squared by n squared matrices. So if you have a huge matrix, then it becomes enormous. Okay? Still, it's what I need. And the first way to do that is I have my matrix A, I just repeat it on the diagonal. There's another way, is to take everywhere the identity matrix and multiply it with a corresponding element of the matrix. So A11 here, it's the corner element of the matrix A, A21 up to AN1. And then these two matrices, it's a simple exercise to see that these two matrices commute. And that's what I need. Because in quantum mechanics in general, if you have problems, it's problems with commutation of operators. And by having two representations at the same time, and they commute, I can solve some of the problems with non-commuting operators. That's the goal. But I will use a tensor notation because it's too much work to write always those huge matrices. And the straightforward one here, I will call that A tensor 1, and the other I will call 1 tensor A. Okay? And then, of course, they commute, and I can write the product as A tensor B. And the matrices of the first type generate what I will call the algebra, and then the second representation will generate what I will call the commutant algebra. And those are algebras of operators working on vectors of dimension n squared, okay? Which is my Hilbert space. It's the complex Hilbert space of the column vectors of n squared elements. Okay, now what I did on the previous slide is a specific example of what is known as the Gelfand-Naimark-Siegel representation. And it's a theorem which is very general, is that every time you have a state on a C-star algebra, you can do the GNS construction. But I did it here in an explicit manner because that will help me on the following slides. And the main advantage of that representation is that I have my state given by a density matrix. I can get rid of that density matrix. And that I want because my ultimate goal is to have a very general theory where there are no density matrices because they give states which are too specific. So how do? I have my density matrix, it has eigenvectors and eigenvalues. In the larger space, I take an eigenvector tensor itself, which is a column vector, which is a little bit complicated. Each element is repeated n times, okay? And I don't want to write that down. I multiply with the square root of the probability, the eigenvalue, sum that, and that's my new vector, capital omega. And you can check it's a normalized vector. And it's a small calculation to see that my state is now given as an inner product of my element of the algebra working on that vector, inner product with that vector again. And in the terminology of physicists, I replace the density matrix with what in physics is called a wave function, an element of the Hilbert space. Okay? And that's an explicit version of the GNS construction. I need something different, and before going to even more technical stuff, let me say what will come. In the roadmap of the rest of my talk, I'm halfway. So I will fix one single non-degenerate density matrix, and then I will consider a second one, which probably will not commute with the first one. That is the problem. And I will solve that problem by going to a matrix in the commutant. So instead of having the second not commuting with the first, I will replace sigma by an operator, a matrix, in the commutant algebra, which will have the advantage that if I now calculate the expectation value with respect to the second one, I get an inner product of where two operators appear which commute, because A belongs to the algebra and the x sigma belongs to the commutant. Okay? And that solves part of the commutation problem. You can show that if you require that operator to belong to the commutant, then it's unique, and it should be positive because my expectations have to be positive. Okay, that's what I did in the paper I published last year. I gave an implicit definition of that operator X, of that matrix. And what I want to show is that if I use Tomita-Takezaki theory, I can give then explicit expressions instead of implicit ones. Instead of having a theorem, there exists a positive matrix X such that instead of having that abstract theorem, I can just write down an expression for that operator X. And then in that paper, I also gave a theorem showing that there exists an exponential chart for that manifold. And now I can just write it down in terms of what one calls the relative modular operator. So let me say something about Tomita-Takezaki theory. It's a theory which dates from the 70s, last century, which exploits the symmetry between the algebra and its commutant. And of course, you could say, yeah, that's quite trivial. A tensor 1 goes to 1 tensor 8. But if I take this symmetry, it's not intrinsic. It depends on representation I choose. But there is an intrinsic definition, which was discovered by Tomita. And what he noticed is that an operator S can be defined which maps an element, a matrix, to its adjoint. But when working on that fixed vector, which I have, that capital omega, so in fact it's an anti-linear operator working in my Hilbert space. Okay? And that operator S then gets the name modular conjugation operator. Okay? And you have a polar decomposition of that matrix with anti-unitary operator matrix J, and then the modular operator is the S adjoint S, which appears here, the square root of that. It's a standard polar decomposition. And the whole importance of that Tomita-Takezaki theory is that it's very general. You can do that on arbitrary C-star algebras and so on, but I will not, I will only at the end say something about that. So I have S and J and delta, and then the Tomita-Takezaki theorem proves two things, which are both highly non-trivial. Is if I have a matrix in my original algebra, then I can define an automorphism group, which in physics is the time evolution. And so I multiply a matrix with power of imaginary power of that delta and the inverse to the left. It belongs again to the same algebra. And that's non-trivial because the operator delta itself, you can write down the explicit expression. It's rho times tensor rho minus 1. It doesn't belong to the algebra. And the second statement is that the operator J maps an operator to the commutants. Okay? And the original proof in the book of Takezaki is about 70 pages long. So it's not very easy to go through all the arguments. For matrices, you can prove it in about 1 page. Okay. And this time evolution is very well known in quantum statistical physics because it's the time evolution we observe in nature. Okay. Good. Then a little bit later, Araki noted that you can generalize that definition of the operator S and of the corresponding modular operator delta. If you have an arbitrary vector of the Hilbert space, instead of having S on A of omega is A adjoint on omega, you replace that omega by the psi, an arbitrary vector, and it still is a good operator. I will not go into details, and you have a polar decomposition. And then I will change notation. Instead of having that psi as an index, I make a choice. My vector psi is my operator in the commutant, square root of that working on omega. And then I have a relation with my second density matrix sigma. And then I use only the index sigma instead of having that psi. So it's a change of notation. Okay, then I can formulate, because I have to be in time. So the indirect definition I had in my paper was that the operator X in the commutant should, when working on that omega vector, should coincide with this operator. And the difficult point is X belongs to the commutant and sigma and rho minus 1 belong to the original algebra. And so that this defines an operator, you have to prove that and check that. But now I can write down explicit expressions with that conjugation operator S. I can simply write down X is this expression. Okay? And similarly, there's a connection between that operator in the commutant and the relative modular operator. And you can also take the square root of that, which is in general very difficult to do. But because rho minus 1 delta, which is standing here, is an operator belonging to the commutant, and sigma belongs to the original algebra, then that makes it easy to take the square root. Okay, that's about the proofs you can find in the paper. Let me shortly say, I don't know, I have still some minutes left. Let me say also something about the exponential connection. So I have exponential connection, exponential arc, or a geodesic, or an orbit. I have my fixed density matrix rho in the manifold, and I have another sigma which is in the curved manifold, and I have tangent vectors. And then the exponential connection is then defined in this way. We have seen that in one of the previous talks as well. You have the difference of the two logarithms is what physicists call minus the Hamiltonian. It's a generator of that geodesic, and you have to subtract the normalization to keep everything normalized. Okay, and that's exponential arc in the terminology we heard earlier today, connecting rho to sigma. Okay, in the context of states on a cyst algebra, the tangent vector is now the time derivative, I would say, in physicists speak, of the state which evolves from the omega sigma to the omega rho at the central point. That gives me the time, that gives me the tangent vector. And so the tangent vector is functional on my cyst algebra. And it is represented by an operator in the commutant, that chi of omega sigma. And it's unique, and so it can be used as a chart for the manifold of states. And it makes the manifold into a Banach manifold. And it's a chart which is centered at the state omega rho, because if that chi is identity, then I have the state omega rho. So that's what I had in last year. And the new proposition is now that the chart is related to the relative modular operators also by a simple time derivative at the origin. Okay? And operators S coming in again. So the conclusion is that it seems that Tomita-Takezaki theory can be used to make the theory more clear. My purpose, of course, is to generalize the whole, what I presented for n by n matrices, to generalize that to the very general case of states on a von Neumann algebra. And most of the work of generalizing has been done already, but not yet published, because it's plenty of technical problems. The problems come from working with unbounded operators, which have domains of definition. That's one of the problems. And the second problem is that a single symmetric operator can have many different self-adjoint extensions. So you have a problem of non-uniqueness. And those two problems together make the whole thing very technical. But I believe it's feasible to do that. And here I want to stop. Thank you.
Any questions?
So you started out by going through the Hilbert space as the wave function criteria. But then when you do the relative one, you get into the Banach space there?
No, everything I told is in the Hilbert space c to the power 2n.
Okay.
So all operators are working inside that Hilbert space.
With a student Hilbert. So you had the Banach manifold word there.
But the manifold is a Banach manifold, which has a precise definition, which essentially means that a neighborhood of any state is isomorphic to an open set around the origin of a Banach space. And that Banach space is not necessarily reflexive, so that's the way Banach comes in.
Any other question?
Please. Can you go back to the definition of the operator S?
I'm sorry?
Can you go back to the definition of S?
Yeah.
The combination of the operator. So it's defined by, because you use quite implicit, you use A in the definition.
Yeah.
That's A omega to A star omega.
Yeah, and so the A of omega, you have to show that it spans the whole Hilbert space in this case, and then you map the Hilbert space to itself, because A adjoint omega also spans the whole Hilbert space. Okay. And S is not in the algebra. It's not a linear operator. It's anti-linear because A goes to the adjoint. Okay? It's not in the algebra. But even if it would be linear, no, you can write. It's difficult. You have to go to a real description to write down what S is, okay? Because it's anti-linear. You have to.
And you said that it's polar part instead of time evolution.
No, with the delta model operator, you define the time evolution everyone uses in statistical physics. So all physicists use that without knowing that it has to do with Tomita Tekisa. I was out of picture.
Since we are running short of time, let's end this speaker again.